Welcome to the Reef Resilience webinar, Helping Coral Reef Practitioners Address Ocean Acidification. My name is Petra McGowan, and I'm the Program Manager for the Nature Conservancy's Reef Resilience Program, and I'll be the host for this session. The webinar is brought to you through the generous support of NOAA's Coral Reef Conservation Program. Today, we're lucky to have two great speakers, Dr. Elizabeth McLeod and Dr. Yimneng Golbu. Lizzie has spent the last decade focusing on the impacts of climate change on tropical marine ecosystems and has played a lead role in the development of the Nature Conservancy's Reef Resilience Toolkit, as well as efforts to coordinate and develop scientific guidance and tools for the implementation of resilient MPA networks, adaptation strategies for sea level rise, and ocean acidification. She's currently focusing on expanding resilience principles to address other systems, including mangroves and seagrasses, and she's working to integrate these principles into MPA planning and management. Our second speaker, Yim's research focuses on the factors that contribute to coral reef resilience and recovery from disturbance, specifically coral bleaching and increasing sedimentation from land use changes such as road building. He has applied his research to improve marine conservation and management and has served on the National Commission of the Republic of Palau for UNESCO and is a board member of the Palau Conservation Society. In January 2012, the Palau National Congress commended Yim for his contributions to the sustainability of Palau's natural resources. We're very excited to have both panelists joining us today. Before we start, I wanted to share some quick information on how the webinar will work. We begin the webinar with the presentations from the panelists and we'll end with questions from those of you participating. There's two ways you can ask questions. You can use the question box at any time throughout the webinar to send questions, and we'll keep track of those for the end of the session. You can also raise your hand during the question portion of the webinar, and I'll take your questions during that time. You raise your hand by clicking on the small hand icon on the toolbar on the left hand of the list of attendees. If you're having any technical difficulties or trouble hearing or seeing slides, you can also send us a question and let us know, and we can try to resolve that issue. So before I hand it over to Lizzie to start, we wanted to get a little more information from those of you on the call today. Can you please answer the poll that is showing up on your screen? How significant of a threat is ocean acidification to reefs? We're curious what you guys on the phone and the webinar feel. So go ahead and answer that question. And then we have a second question for you as well. So you'll see another poll hopping up in a second, and you can see the results of this first poll. So some of you are ranking it as the most significant and presenters, so you can kind of get an idea of what your audience is ranking the threat of OA, and major and medium threats. So most people ranking it as a major or medium threat. And our next quick question for folks is, do you know of specific management strategies to address ocean acidification at your area or site? So please let us know, get an idea of how many of you actually have an idea of specific strategies that might be used. And we'll see the results of that poll. So Lizzie and Yim, as you can see, you've got some folks knowing some strategies and some folks not, and so I think you'll get some interesting questions today. And Lizzie, I'm going to hand it over to you.
Perfect. Thank you so much, Petra. And thanks also to Sherry and Jordan for pulling this together. And thanks everybody for tuning in to learn more about ocean acidification and some of the ways that we're trying to tackle it in our program. So today I want to go over, many of you already know what ocean acidification is, or you may have read about it, but I just want to do a quick refresh on what it is, why we should care about it, and what we can do about it. So ocean acidification is a reduction in ocean pH due to the increase in anthropogenic CO2. So carbon dioxide is emitted through fossil fuel emissions, and there are many, many greenhouse gases that can go into the atmosphere, but it's specifically the CO2. So ocean acidification is a reduction in ocean pH due to the uptake of anthropogenic CO2. So again, it's the carbon dioxide in the atmosphere that actually dissolves into the ocean and changes the ocean chemistry. So this graph I wanted to show you is looking at parts per million of atmospheric CO2, and it goes from about 1960 to present. And the big take-home message here is that CO2 in the atmosphere is increasing, and it is increasing dramatically. And we're currently 30% higher than we've seen in the last 650,000 years. And actually, at the end of March, we just crossed 400 parts per million of atmospheric CO2. The next slide I want to show you looks at atmospheric CO2, but as it compares to CO2 in the ocean. So the point here is to look at, again, we've got about 1960 to present. And you see that as you have an increase in atmospheric CO2, there's a corresponding increase in the CO2 in the ocean, and then there's a corresponding decrease in the pH. And so that means that as you're getting more and more CO2 in the ocean, you're actually getting a lower pH and more acidic. So for those of you that are interested in the chemistry behind ocean acidification and what's happening, the CO2 dissolves in the seawater and it forms carbonic acid and a release of the hydrogen ions. The hydrogen then combines with carbonate ions to form bicarbonate, and then the formation of bicarbonate removes carbonate ions, which makes them less available for marine calcifiers. So the point here really is that there's two processes that are happening that are making it difficult for calcifying organisms. One, we're getting more acidic in the ocean, which can lead to the actually dissolving of the skeletons in shells. But two, there's actually less carbonate available to build and make those skeletons and shells. So it's kind of a double whammy effect. The next graph I want to show you is looking at global sea surface pH change over time. And this one is coming out of the latest Intergovernmental Panel on Climate Change, or the IPCC report, looking at what are the projections in ocean surface pH by the end of the century. And the thing to notice here is that if we continue as we are going to have a major continuous increase in CO2 emissions, which is actually going to drive a very steep decline in our pH or increase in our ocean acidity. However, if we're able to control emissions and to actually limit the carbon dioxide going into our atmosphere, we'll be able to follow that light blue trajectory and actually keep the pH in our oceans fairly stable. So the point is that reducing CO2 emissions will slow the progress of ocean acidification. So this image right here is looking at pH globally from 1850. And the point here is that generally at this time the open ocean pH was pretty much around 8.1, 8.2, 8.3. And you'll see some areas in orange. These are upwellings where you actually have upwelling of more acidic water. So you might see some lower acidity, some lower pH in those areas. But the projections are that by 2100, we're actually going to have a 0.3 unit decrease in pH. And that may not sound like a lot. 0.3 units doesn't seem like a big deal. But actually, the pH scale is logarithmic. And so a 1 unit change corresponds to a 10-fold increase in acidity. So we're actually looking at doubling the acidity of what we currently have now. And again, those upwelling areas are going to have even lower pH. This image here shows the aragonite saturation state in 1850. And you might have read about aragonite saturation state. And aragonite is just the mineral form of calcium carbonate, and it's what corals use to build their skeletons. And typically we think of corals really needing to have above a 3 in order to calcify and be healthy and have enough carbonate ions in the water to build their skeletons. But what you see here is that most coral reef areas pre-industrial revolution were above 3, but when we get to 2100, our models are projecting that we're actually going to be below 3 in those areas. And also you'll see in the red corrosive waters where you have a major decrease in the aragonite saturation in our polar and our temperate region. So what this means is that, phytoplankton, calcifying organisms in these areas are actually going to be more vulnerable to ocean acidification than organisms that are in the tropics. Okay, so we've talked a bit about some of the organisms. We talked about corals as being really important calcifying organisms. Crustose coral and algae is another one that helps cement the reef framework together. Sea urchins, mussels, clams, oysters, halimeda, pteropods, which are an important food source for a lot of our commercial seafoods. And actually, studies are coming back showing fish, and particularly clownfish, have changes in their ability to sense danger from increased ocean chemistry. So when you're communicating, when you're talking to your stakeholders and your colleagues and your friends about ocean acidification, it's not always useful to show a graph or a chemical equation to try to make the point. And I was Googling online looking for different cartoons about ocean acidification, and I really liked this one. I thought this did a good job of really showing the main point and what's happening. So in the first image, you've got a boat of scientists that are all screaming and they're all excited, yay, because CO2 is going into the ocean, which meant that global warming is actually being buffered. All of that atmospheric CO2 a lot of it is being dissolved into the ocean, so global warming is actually happening at a much slower rate than it would had the ocean not been taking it up. But then they all freak out and scream, ah, when they realize, unfortunately, CO2 is mixed with water and we get more of acidic oceans, and then that has bad implications for organisms and animals such as oysters, corals, urchins, and clownfish. So as it's bad news for the marine organisms, it's also bad news for those that depend on them, like people. And then again, that this process is accelerating and it's likely to continue. So I thought this was a nice graphic to just summarize some of the main points. But again, what the science is telling us is that in general, with marine calcifying organisms, we are seeing patterns of reduced growth, reduced calcification, reduced fertilization, weaker skeletons and shells, increased sensitivity to bleaching, increased sensitivity to storm impacts, because as you have a more vulnerable, you have a weaker coral skeleton, it's more vulnerable to breakage following storms of corals. More fleshy algae, and then we have impacts up the food chain. We talked about pteropods being vulnerable to ocean acidification, and then the species that eat them are also vulnerable. So we have a decreased abundance of commercially important shellfish. This is actually really important. This is not something that's happening 100 years off. This is something that there's actually folks in aquaculture right now in Washington State, the Pacific Northwest, that are actually already noticing declines in growth rates, and it's actually already affecting their industry for important shellfish. So it has also food web implications, as we talked about, and then also if we lose our reefs, we lose all of the values that they provide, such as coastal protection, supporting food and livelihoods of coastal communities, cultural and spiritual importance of reefs, etc. So what's the good news? We've talked about the bad news and what the sort of downward trends are, but one of the exciting things that's coming out of the research now, this is a paper that's written by a friend of ours, Christy Croker, and it came out in 2013, and it's a meta-analysis, which means it takes all the data from a bunch of different papers that have been written, and it tries to come up with, what are we looking when we look at all of these data sets together? What's the big picture? And the big picture here is if you look at the red and the pink colors, those are generally doing worse off for ocean acidification. And then where you see the green, they're actually enhanced with ocean acidification. So the take-home message from this is that different groups are responding differently. Generally, your calcifying organisms, your corals, your calcifying algae, your mollusks are going to do poorly under ocean acidification conditions. But actually, some fleshy algae and diatoms, particularly your phytoplankton, are actually going to do better. And then your gray is showing that there's, too few studies are not tested, which indicates, this is a new area of research, so there's a lot of work that still needs to be done. But these are just some of the kind of the take-home messages that are coming. So we have winners and losers. The losers often discussed are a lot of commercially important shellfish, corals, and a lot of the winners are likely to be some seagrasses, some seaweeds, some fleshy algae. But on the bottom left, I want you to notice that picture, which is actually an exposed reef. This one's off the coast of Australia. And one of the really cool things, I think, that's coming out of some of the research in the last couple of years is that we're finding that in some of these back reef lagoon areas and exposed reef areas, corals are actually living and thriving in acidic conditions. And this is some of the research that's coming out of Palau. And Yim is going to talk a bit more about that when he does his presentation. But it's something that gives us hope for the future, is that it's, not all coral reefs are responding poorly. So what causes these differences in variability in how different taxa respond? Well, there's different variability in pH in the ocean. So this is a slide, this is some research that Nicole Price, who's actually on the phone with us today, and Gretchen Hoffman have done, looking at the pH in the open ocean in the temperate eastern Pacific and tropical central Pacific. And the take-home message here is that your pH in the open ocean is generally pretty stable. When you zoom into a coral reef, this is in Moorea and Palmyra, you actually see quite a bit of variability. In addition, if you look on the bottom right-hand side, you see daily pH fluctuation. On a daily scale, you're actually seeing quite large changes in pH on a particular coral reef. And what's important about this finding is that we're seeing that on some reefs, they're actually changing as much in one day as are projected to be changed in the ocean, in the open ocean, by the end of the century. So when we have these global ocean models that say by 2100 we're going to have a pH of X or a aragonite saturation state of X, we're actually seeing those changes already on some reefs. And in some cases the corals are able to cope with it, and they're actually doing quite well, which is exciting for us. And the top image is looking at shallow reef versus deeper reef. And so this is basically showing that you have differences in pH variability among different reef communities. And one hypothesis might be that maybe this deeper reef has more contact and more flushed with oceanic water. We talked about that oceanic water typically being more stable in pH. So maybe it sort of mutes that signal, whereas on your shallow reef, it's driven by a lot of those reef processes such as calcification and dissolution, photosynthesis and respiration. So you might see a greater fluctuation there. So again, these reef processes can affect ocean chemistry at local scales: photosynthesis, respiration, calcification, and dissolution. Again, your benthic community can also drive those changes, because your corals, your seagrasses, whatever your benthic community is going to have different rates of photosynthesis and respiration, different rates of calcification, and that will all have an impact on how much CO2 you have in your water column, and then therefore how much pH, what your pH is. We talked about water movements, whether you have a lot of flushing with oceanic water, or whether you have these back reef lagoon areas where you may have water that just sits, and it just sits and bakes on that reef, and it's not well connected with oceanic water, and it's really driven by those local processes. Temperature, salinity, and nutrients can all affect your ocean chemistry, and also human impacts. Humans actually, through agricultural pollutants like nitrogen oxide and sulfur oxides, can actually increase the acidity in coastal waters. So that's enough of the sort of the variability, and let's get to action, what we can do about it. So we're building on a lot of the lessons that we've learned from coral bleaching. One of our main strategies is to try to identify refuges, or areas that are naturally positioned to survive. So our idea with ocean acidification is, can we find natural refuges, places that are either experiencing acidified waters and are coping, or experience high variability and they've built up resistance, but regardless, these corals are thriving in these conditions. And if we can find these areas, we want to ensure that we're protecting them from all of the other stressors that are facing coral reefs. Incorporate them into our marine protected areas, and then connect them so that they can help certain areas that have been damaged recover following disturbance events. We also want to control stressors that affect pH. So we talked about some of those chemicals that come in, the nitrogen and sulfur oxides, and that enhance algal growth, because again, if we have increases in acidity stimulating fleshy algae, we want to make sure that we're not exacerbating that process with other things. So this is another cartoon for you. I saw this. This is actually coming out of Washington State, and this is a total joke, right? Dumping Alka-Seltzer in the ocean. What a ridiculous idea. But I put this in here because I got a call from a researcher in California about 2 years ago who's spent years looking at just such an idea, where you crush up basic material. So he's looking at limestone, and there's also olivine and some others, and actually put that into the coastal system and do that to buffer changing ocean chemistry. And so we started a conversation, and through this conversation it became clear to me that what may sound like a crazy idea today may be our most viable option in 40, 50 years. And so I think, you know, we have to always keep in mind that some of these cutting edge, outside the box ideas are going to be really important for us to consider, to test, to look at the costs and benefits, so that by the time we do have more limited options in the future, if we can't get control over emissions, that we've really put in the science that's needed to make smarter decisions down the road. But in the interim, we are going to keep doing what we do to manage reefs as well as we can to cope with climate and other impacts. So we want to control stressors like sedimentation, particularly pollutants that come into the system that will actually increase the chemistry, the acidity of the coastal waters. We want to keep our reefs as healthy as possible so that they're better able to cope with changes in ocean chemistry and increased heating stress events as well. And we want to maintain our herbivore populations because, again, if we get this increased growth of algae, we want to make sure that we're able to control those algal populations so that corals have room to settle and grow. We also want to control our own CO2 footprint. And then finally on the bottom right, you know, I hear a lot of managers and planners say, you know, controlling, you know, stopping fossil fuel emissions, particularly stopping CO2 mitigation, is beyond the scope of what a manager can do. And I really truly believe that managers have a central role to play in building the case and in influencing local and national level decision makers that we have got to address this problem at its source. All of these other strategies are band-aids. If we don't control CO2 emissions, we are not going to solve this problem of ocean acidification. And again, think back to the graph I showed at the beginning where you've got that dark red line going down and seeing large changes in pH, and then controlling emissions where we have that light blue line that really keeps pH in a healthy place for corals and coral reef ecosystems. So I do think it's an important role for managers to play that we continue to make that, build that case. So I want to end with some of the work that the Nature Conservancy has been doing. We have really spent, I would say, the last 4 or 5 years recognizing that we cannot go this alone. We don't have the expertise in-house, and we really need to rely on global research institutions, experts in ocean acidification and coral reef ecosystems, and form strong partnerships so that they can help us and we can bring the best science in to inform our conservation work. But that we can also share our needs as conservation planners and managers with the research community so that we can actually influence that research. And that effort has really led to some really fabulous collaborations with Woods Hole, with Katie Schamberger, Ann Cohen, and Hannah Barkley, some of whom are on the call tonight, who've really been doing some pioneering work in Palau, trying to help us not only understand what's happening with ocean acidification, but how we can actually use that information to inform the protected area network there. We'll be hearing more about that from Yim. So another piece too for us is we want to get this information into the hands of practitioners. And so we do that by putting the content on our Reef Resilience Toolkit. So we recently built out a section on ocean acidification on the toolkit. This is a work in progress. You know, this is something that we're relying on our research partners to help us improve and put the cutting edge science in, and then work together to raise funds that are applied, that have actual conservation applications that aren't just pushing the research forward, but we're actually steering the research so that it's something that comes up with tangible outcomes for us. So I want to stop there and turn it over to Yim to share some of the really fantastic work that's been going on in Palau. Thank you.
So in Palau, Palau is an island, and the people of Palau are very dependent on their marine resources. And Lizzie talked about the importance of reefs, and this is very personal to the people of Palau because our livelihood really depends on it, and it's important to our culture and to our way of life. And more recently, it has become very important because of the tourists and the visitors that come to Palau. Almost all of them come to Palau because of the coral reefs and our marine environment. So it's important to us traditionally, and then in the modern times it become very important as an economic activity, attraction for tourists and driving a lot of the tourism business in Palau. And so the people of Palau has always cared about the marine environment, and because of its importance, they've always tried to find ways to protect the marine environment. In 1956, the first marine protected areas in Micronesia was established in the Maruguit Island, or the 70 Island, the rock islands of Palau. And then in 1976, Marumbao, the spawning area, which is the spawning aggregation for groupers, was protected. And since then, a lot of, in the early 90s, a lot of protected areas were established. And this was a way for the people to try to conserve these very important resources. And then in 1998, we had a big bleaching event, and about 30% of the reefs in Palau were destroyed from this bleaching event. And it turned many of the very nice reef into rubble. And so this was like a wake-up call for the people of Palau. That even though we've been going around setting these protected areas that mainly were set aside by communities to conserve the fisheries resources, it didn't help when it came to bleaching. And so started to think what are the issues and what are the things that we can do to address this. And so when we were looking at this, we found that the protected areas is really set aside by communities. So there was no big plan of how to set up the protected areas. It was individual community deciding to set aside areas for protection. And because it was really focused on the community, it didn't take into account the whole nation, and maybe some, it didn't really look at Palau as a whole nation and look at what's being offered around Palau. And then, of course, because of the 98, we found that we needed to look at things such as resilience and ecological integrity of the sites. And that the system that we had, where it just created protected areas by communities, you wouldn't deal with the impact of this climate change, such as the bleaching, where we saw a lot of our reefs destroyed. And so that led to the PAN, the Protected Areas Network. And the idea of PAN is to look at the whole Palau and to look at the overall diversity and to design this network of protected areas so that we have a bigger picture instead of just looking at small communities. So that's one of the objectives of PAN. But of course, the second objective of PAN was to continue to support local communities in their efforts in protecting natural resources. And PAN also allowed the partnership between the national government and the local community, so that we can have the local communities which is very focused on their areas, and then the national government looking at the whole of Palau. So some of the work, so PAN is very dependent on science and also on monitoring and incorporating this new information and this research into the design and how to design this network that take into account all the science that is being done. So this is a picture of the main Palau Island, and this was some of the work looking at how the reefs, what were the condition of the reefs, and how were the reefs recovering from the bleaching event. And when we look at this, we found that there are areas that seems to recover well, and that not all areas are recovering the same way. So there are areas that seems to do better than other areas. So that was very interesting, and this can help us as we work on the design to incorporate those areas that seems to be recovering faster. And then in 2010, we had another bleaching event, and then we look at the areas that were bleached, and we found the same thing, that some of the areas did not bleach and some of the areas did really well. So this is also information that we can help us as we are thinking about designing the protected areas network. And then this is a study of by Schemberger and Cohen and others from Musol, and this is what Liz mentions, that there are areas that
Yim, sorry to interrupt.
Seems to do really
this
well,
is Petra. Sorry to
even though
interrupt.
they live in very acidic environment.
Yim, sorry to interrupt. I just wanted you to know that there's problems seeing your slides, so most of the audience cannot see your slides as you're talking through them. But I think you should just continue, talking through your main points, and we'll continue to try to see if they come through. but I just wanted you to know that they're not able to see your slides as you're going along. Sorry about that. Okay. But continue on, but just so you know what everybody's seeing. We're having people see different things, but your slides are not moving forward. So.
Okay. All right. Okay. Okay. So I'm at the slide. So this is a picture of the two very different communities. One in Nicobe and one outside. And usually when we think about areas that live in low acidic environment, there's no corals, things that at least we talk about. But here we have a very diverse coral communities. And it's one of among the most diverse reef in Palau, and very high coral cover. We have very high coral cover, and yet this is living in a very acidic environment. So this is the same thing that Lizzie was saying, that there are areas in terms of bleaching and now with acidity that we find these areas do better in dealing with oxidative stress. So we have this network now, and I'm showing a map of Palau with all the protected areas. There are 14 sites right now that are in the PAN networks, and there are 31 sites that are protected. And so we're working now to incorporate these sites into the protected areas network, and then to put in new sites to make this network complete and have the network incorporate all these special sites. So that's how all these research are feeding into management, that they're identifying the sites and they're identifying things that we can look at that might indicate sites, resilient sites, and then we incorporate those sites into the network. So we also been doing some modeling using a hydrodynamic model to look at coral connectivity. And so so I have a slide of showing how the existing marine MPAs are connected. So we've identified gaps. And so the idea is that we need to add new sites to fill in the gap so that all the protected areas in the pond are connected. And so if something happens, let's say a bleaching or acidity that affect the other areas, then the sites that seems to do well in terms of bleaching or acidity will still be there. And then because the network is connected, the larvae from those sites will be able to go to the other sites and fit into those sites. So in terms of coral connectivity and in terms of fish connectivity, there's different types. The fish are more connected than others, and corals are more self-seeding. But we need to ensure that this network is connected so that areas that are resilient or areas that do well, do not bleach or again deal with acidity, can provide seeds to other areas in the network. And then we also connected Palau, while Palau is connected and there's a zone of self-seeding where a lot of the areas, a lot of the reefs are self-seed. There's also a large dispersion, and this is between Palau and Yap, and we're starting to look at other areas in Micronesia. And so while we're working in Palau, I think that this kind of work have applicability, and then we can transfer this work to the other islands in Micronesia. And as some of you might know that Palau is part of the Micronesia Challenge, and that we realize that we are connected, and we've done some work to show that Palau and Yap are connected, and now we're looking at other islands in Micronesia. And so that the work that we're doing in Palau, while it might also affect other islands in Micronesia, but also that we can transfer this and go to the other islands in Micronesia and help with the design of their network. And there is some efforts in our neighbors in the Federated States of Micronesia trying to design and discuss a protected areas network. So this way we can transfer the knowledge and help them in their efforts because of our experience in Palau. So that is all I have, and all of the work, all the science, and all the management efforts is really trying to ensure that we continue to have these resources. And my pictures, I have these nice pictures of the different habitats in Palau to show that if we do a good job, then all these habitat can continue to exist the way they are and contribute to the life of people in Palau and maybe other places that are very dependent on coral reefs. Thank you very much.
Thanks, Yim. I'm sorry, everyone, that we could not see those slides. We have tried very hard to deal with the connectivity issues in the past week, and unfortunately it did not work out. But we will work on getting Yim's slides and putting them with the follow-up materials to the webinar that we send out afterwards. So what we wanted to do was take some questions right now about for the panelists, and you can raise your hand or chat any questions you may have for Lizzie or Yim, and I can call on you or answer your question if it's chatted. So I have one question here from Abigail. I'll try to call on you, Abigail, to ask the question yourself if you'd like. Are you there? Abigail Moore, would you like to ask your question? All right, I will ask it. So the question is, she would like to know about the species composition and structural complexity of the resistant and less resistant sites. Do they look, or are they similar, or are they not? What are the differences? So I think this is a question for Yim. Yim, are you there?
The reefs are very they're very complex. They're very high diversity. Yes.
Oh. Petra?
Yeah?
Sorry, we've also got Hannah Barkley on the phone, and she might, if we can unmute her too, if when Yim is finished, it might be good to connect to get some of her input as well.
Okay, great. So go ahead, Yim, and then I'll call on Hannah. Yim, go ahead.
Yeah, so the reefs are very diverse, and like I said, they have high coral cover, and they're also complex. A lot of different corals in there. The only big difference between this acidic reef is that they don't have as much acropora, let's say from these reefs and the outer reefs. But they do have branching corals. They have Porides cylindrica, they have Porides ras and other branching corals. So they have a lot of anacopora. But so the communities, the species composition, of course, is different from outside, because outside it's dominated by acropora. But it has a lot of genus of corals are found there, and all the shapes are found there, and yeah, it's very diverse reef communities. And we've done surveys all around Palau and across Micronesia, and these are some of the highest coral cover reefs that we've ever encountered anywhere.
Great, thanks, Yim. Hannah, I've unmuted you. Do you have anything to add to that?
Can you hear me?
Mm-hmm.
Excellent. Yeah, I think I would just echo what Yim said, is that with the declining pH that we're seeing, moving from the kind of exposed high pH barrier reefs to the low pH lagoonal rock islands reefs, we're actually seeing a tripling in coral cover, a huge increase in the number of coral species, and no change in the diversity. And as Yim said, tons of different kinds of structural corals, branching corals, Porides. So despite the fact that it's extraordinarily acidic, we're seeing hugely diverse high coral cover reefs with some coral species that are only existing in these really acidic environments, which is pretty incredible.
Great, thanks, Hannah, for adding that. Next question is, have you explored kelp farming to absorb nitrogen, lower OA effects, and potentially provide a local source of income? I'm not sure, Lizzie, if you want to go for that question, or?
I would like to bunt that to one of our experts. I don't have a good answer for that. I would hope that we have Nicole Price on the phone. Nicole, do you have any comments there, or any of our other OA researchers?
Hi, can you guys hear me?
Nicole?
Can you hear me?
Yeah,
okay, good.
I just unmuted you.
Thank you. I don't know much about kelp farming per se, but I'm also curious about algal farming in general and the potential of downstream effects that the primary production from algal farming could have on reefs in terms of CO2 fixation. But there's another side to algal primary production that needs to be considered. The concern I have is that not all algae hold on to the carbon that they fix during photosynthesis very efficiently, and some leak this carbon out in the form of dissolved organic carbon, or essentially sugars, to the water column, which can then have knock-on effects for bacterial blooms in the water column, which in turn have higher respiration rates, and in effect you have the opposite effect on the water column that you would expect from having higher rates of primary production. You actually end up having higher amounts of CO2 due to the knock-on effects to the bacterial populations associated with large algal blooms. So I think there needs to be a lot more research into the potential positive effects of raising primary producers for fixation of carbon dioxide before we launch into a lot of effort to create these farms. But the potential for them to have a economic benefit is also intriguing. So basically, I guess the answer is we need more research. There's not a lot of information yet about the knock-on effects of kelp farming. There's also the potential for invasive species of algae to be introduced into regions where they didn't exist before, which can have large negative direct impacts on coral populations. So it's an interesting idea, but needs to be studied much more before we try it.
Okay.
Can I add to that, Petra, real quick?
Yes, please, go ahead.
One thing to add, I know, just in terms of kelp farming, I know one of our marine scientists based in California is really interested in growing that part of the Nature Conservancy's work out there, is to look at the impacts of ocean acidification on kelp, and then potentially look into the feasibility of kelp farming. But as we've been thinking about it in terms of tropical coral reef systems, we were looking at areas where you have seagrass communities potentially that were upstream from coral reef areas that might be scrubbing that carbon dioxide and downstream to the corals. So in those areas we would give priority protection to corals that were downstream from these seagrasses. So taking that to an aquaculture standpoint is sort of the next step. I think there's active research going on in Indonesia and some other places looking at the potential for that. But I think it's an area that people are really interested in, and hopefully an area that we'll get some guidance from the research community on.
Great. Thanks, you guys. Another question is, can you speak a little bit more about the communication on ocean acidification? And it's a very general question, like that's what it is, but speaking a little bit more about general communications on OA, and perhaps what are the most effective things that you are feeling are working, either with stakeholders or policymakers.
Yim, you want to take the first crack at that for talking about it in Palau?
Yeah, it's very hard, and I've always thought that how can we best explain acidification, just even acidity and pH, and trying to explain that in Palau, so don't even try to say pH and things like that. But I think what we've been saying, and this might not be 100% accurate, but people respond to it and they understand when we say it's the, oh, somebody's dog is barking. Yeah, when we say it's So when we talk about acidification, he said it's sour, like a vinegar or like a lemon taste. So we're saying the water is becoming sour, and then we try to explain how is that happening, and then the people seems to understand that and respond to that. But yeah, like bleaching, when corals turn white, it's easy for people to see. And when you say, yeah, during the bleaching when the coral turns white, and they say, oh yeah. But when you say the waters are acidic and stuff, then it's hard for people to think. So we're trying to. But what I find out that also is that if you take the time and like this, we do a lot of community meetings and this one-on-one. Then people, after those meetings, I really have a sense that people really understand and they're really concerned about these issues.
Great. Thanks, Yim. Lizzie, did you have anything you wanted to add about communication?
Yeah, real quick, there's a link we can send afterwards. I just saw a video done by Steve Palumbi at Stanford, and I thought it was one of the most compelling. I mean, I've had to do a lot of talks about ocean acidification where, you know, you show the chemistry, the chemical equations, and it's really boring, actually, and it doesn't resonate with most people you talk to. And I think the most compelling visual I saw was actually Steve taking a piece of coral, a live little acropora branching coral, and sticking it in a cup of acid. And it's just regular, vinegar that you get from your kitchen, and just watching what happens. And it was so compelling, and it just, obviously it's more acidic than the oceans are going to be, but it gives you a very visual understanding of what it does to the coral tissue, and you can actually see little bits and little filaments in the solution, and you can see it in a very quick amount of time making a change. So I often think if you have the ability to do a live demonstration, I think that can be very compelling. But I really like what Yim said about, you know, souring the ocean, and I think that's something that folks are starting to use more and more to try to convey the idea. I think the other piece to convey too is that it's not 100 years out. You know, we're already seeing very acidic conditions on reefs in places. We're already having industries impacted. So I think that's another really important message that needs to be conveyed, is that this is happening now. This is not something that's way off into the future.
Great. I'm going to call on Rod. Rod, do you want to ask your question?
Hi, yeah, thanks Petra, and thanks Yim and Lizzie for your talk today. I really regret that I was one of those people who couldn't see your slides, Yim. But I had a question which on hearing Hannah's comment, I revised completely, and it made me think that we ought to be putting attention into identifying these pockets of OA resistant, if that's the right word, areas where there's been some adaptation within the communities to grow and thrive in areas of higher acidity. And with the point of view of doing what they're doing now with some of the staghorns, with some of the elkhorn and staghorn corals in the Caribbean, where they're growing them and they're transplanting them out, and they are collecting corals, you know, across as wide as possible a genetic framework as possible, and using those to restock, to repopulate areas that where the staghorns have been taken out. And you know, it might be more realistic as a hands-on intervention to do something like that, rather than to go the metaphoric route of pouring Alka-Seltzer into the seas, you know, doing some kind of chemical intervention. And I think that would be quite a doable thing. And you know, so researchers like Hannah and Co. and those Woods Hole guys and Pickrick and Yim, who are finding these pockets of low pH where corals are thriving, I think those are areas we really need to focus our management attention on.
Lizzie, do you want to add anything to Rod's comment, or?
Yeah, no, I absolutely agree, Rod. I think that's an excellent comment, and I think that you know, there's already work going on looking at sort of selective breeding of OA resistant, I think it's Sydney oyster or something, one of the commercially important shellfish. But I think that, you know, that is definitely part of this suite of active intervention strategies. And I think, you know, Yim and Hannah and Anne's and Nicole's work are really pushing that science forward in ways that really has really excellent implications for us as managers. So maybe we can turn it over to any of them to add in.
Okay, and I also have more questions to ask from people. So I've unmuted. Who do you want me to unmute, Lizzie?
Hannah and Nicole, please.
Okay. Unmuted. Any comments, either of you?
This is Hannah. I think that Rod makes a fantastic point, and that's something that we've been really, really interested in, figuring out mostly like the mechanistic basis for the acidification tolerance we're seeing, and then once we unravel that, figuring out what sort of implications that has for conservation strategies, or is it possible that the corals that are doing really well in these acidic reef environments could be able to repopulate areas that are devastated by ocean acidification in the future. And so that's something that we're really trying to look into and understand in our research right now.
And I'll just add to what Hannah said and the work that she's been doing in Palau, which is really great. From work that we've been doing in the Line Islands and including Kiribati, we see that when reefs are experiencing multiple stressors, they kind of start to lose that ability to resist or create refuges from ocean acidification. So I think the next wave of research will really be about how reefs can deal with multiple stressors, including acidification, and when and where we can, in a sense, build up their immunity to at least ocean acidification by managing the other stressors that we have more established methods of doing it, at least at a local scale.
Okay, thank you guys. So I have another question from Derta in Indonesia. Derta, I'm unmuting you. Can you ask? Do you want to ask your question? It's a great one. Or Derta, do you have audio? Okay, I'm going to ask it for you. So Lizzie and Yim both, I think, might have some good ideas on this question. Derta's curious about leveraging funding. He says that in Indonesia, OA is not like a sexy program. It's not something easy to get money for. How do they engage funding for, funders and people to have concern for this issue? Any ideas?
Yim, you want to go for that?
Well, I think for us is we have partners, and then it's those partners that have found resources to do this kind of work. So, for example, Woods Hole, they came with their own. They had TNC and Tiffany Foundation, and they had others, I think, that help with some of the work. And then also there's other, some of the research looking at Symbiont from with Todd Lechance and Mark Warner. Those were funded by the NSF, and I think also our school was funded by NSF. So I maybe Rod would know better answer to that than me.
Just
go ahead, Lizzie.
Yeah, just real fast, because I know we're running out of time. I think for us it's been a real challenge. I think it's a great question. I think the challenge is that you don't see it. It's an invisible threat, unlike coral bleaching where your reefs turn white. And it's very difficult to raise money for something that people can't see when you have these other major pressing issues like overfishing, destructive fishing, etc. One of the ways that we've been able to generate funding has been largely through partnerships with research institutions. So we get researchers who are already doing this kind of work, and we try to influence their work to have relevance for conservation. But I think it's an excellent question, and I think it's a real challenge. Rod, did you have something you wanted to add to that?
He's muted himself, I think, Lizzie. So unless he, oh wait, there he goes. Go ahead, Rod.
Oh, there, I'm unmuted now. Sorry, I didn't mute myself. Yeah, I agree entirely with what Lizzie said about the partnerships. And to Derta, I would recommend that you are open to forming partnerships with researchers. I mean, there are a lot of researchers out there in the world who would love to do research in Indonesia. And by partnering with Reef Check on some of the sites where you guys are working, you can open the doors for that kind of research and let them come in with their money and work with you at your sites and provide the answers you need. Thanks.
Great, thanks, Rod. All right, so we have time for one final question. Yim, what are some of the biggest challenges that you've encountered in Palau in incorporating this OA considerations into your MPA networks? Yim, did you hear that question?
Well, I think it's yes. There are many different factors, and Palau is a small area. So we have OA, but a lot of people are concerned about fish, and a lot of people are concerned about clams and chocus and all this. So I think it's one of the issues that we need to consider with a lot of issues. But we've been very lucky that we've been working with the TNC office here in Palau and with other people, planners from JCU that can help us put all this different information into the spatial planning and then give us options that we can look at and discuss and select the best sites. But I think also another issue that we need is we need to move from sites to like predictions, like what are the characteristics that we would look at, that we need to look at, so to identify other sites, and then also to have a more a way to generalize the data, because you can have so much data in one area, but when we look at the whole design of the whole Palau, we need to have a better idea of the whole thing. So yeah. I think those are kind of issues that we have to deal with. And as the others have said, you know, it's really the partnerships with the other people that can really help us address these many different things.
Great. Thanks, Yim. And thank you, everyone, for joining us. If I did not get to one of your questions, which I did not get through all the questions, please feel free to email Lizzie, or I believe Yim's email is there, or Lizzie's there, and she can always follow up with Yim. But they will take any other questions that we did not have time to answer. And I wanted to thank our presenters. The recording of the webinar and the resource links will be sent out to our email list after the webinar today. If you're not on the list and you'd like to be, email us at resilience@tnc.org and send us any suggestions for future webinar topics that you think would help you with your work. We appreciate your participation and hope you can join our next webinar on May 8th. It will be the first in a series of 3 webinars to share information on the development of new tools and management strategies for coral reef fisheries, and look for that announcement of the webinar with more details coming up soon. Thanks for joining us.